Hello and welcome to another Solana tutorial. This is part 5 of the Solana development course, and today we're gonna talk about deserialization of custom account data. And this is in fact probably my favorite topic of module 1, just because you need that so much when you're a Solana developer. I'm excited about this. I'm sure that you can learn something in this video, because I think I'm gonna go a bit more into depth than James does in his course. So not only do I want you to be able to deserialize with Porsche, I also want you to understand what's happening behind the scenes. And we're gonna talk a little bit about that as well. So yeah, let's go and jump in. Okay. James, what are we gonna learn today? By the end of this lesson, we even learn about PDAs. Oh, such an important topic. Program derived accounts, PDAs. If you're a Solana dev, you definitely heard about this, and this is one of the important concepts. Derive PDAs from specific seeds, yes, so we create them as well, not only explain what they do. And we're gonna fetch a program's accounts, and we're gonna deserialize custom data. Cool stuff. And then I want to add, we're gonna understand how the deserialization works, or what actually is being serialized and deserialized. Because last time we did the serialization, and we saw that this Porsche library pretty much does it all for us. But today I want to go a little bit more into depth of what's actually happening. Right? How the serialization works, and therefore how the deserialization works. Okay, so TLDR, PDAs are addresses that do not have a corresponding private key. Now, I did already make a video about PDAs, and I went into detail there, so maybe we keep that somewhat short, but not too short to not understand it just based on this video. The concept of PDAs allows programs to sign transactions themselves and allows for storing and locating data. Storing and locating data can also be done with regular accounts, but then you always need to put in the same account. It's much more helpful if the program can derive an address based on some seeds, so some information that you put in, and on that address, it can then store stuff, and for that account, it can also sign. That's the very most important thing about PDAs, and why they are so useful is because programs can sign for those accounts. So if you have a normal wallet account, like I had here in my software wallet, I have a regular account, right? And I, having the private key, can sign for this, and signing means that I can send out some sol or tokens or, perform any other actions. Now, PDAs do not have a private key, so there cannot be a private key that can sign for this account. And because of that, they can be used for programs to actually sign. So the programs need to get a specific address where there is no private key for it, and that can be done with this find program address method. So that's how we derive a PDA. We get the program address, so the account address plus a bump. We will see what that is later. That essentially just finds a random address, and it could happen that there is a private key for that. And in that case, we need to add a bit more to the seed such that there is no private key for this address, such that we can use it as a PDA. You can get an array of all the accounts belonging to a program using get program accounts. Now, that is a method that has been in the news because it is not a very efficient way. Getting all of the program accounts for one program is not particularly efficient. Therefore, just by the way that accounts are stored, if I find my program address, then I can jump there directly. So some RPCs don't even support this. Some have strict rate limits for it because it's just such a method that takes up a lot of resources on the RPC. We try to avoid having to do this. Sometimes we have to, especially for big programs like, say, the token metadata program. If you use get program accounts on such a popular program that has a ton of accounts, then super resource intensive. Thus, we try to avoid that actually. So that's private opinion now, but we try to avoid having to use this. So account data needs to be deserialized using the same layout as it is stored with. Well, obviously, if we serialize something, the way to deserialize it is using the same schema. And we can again use the Borsche library to create such a schema. I want to make you read, and I want to this time have good audio quality because people were requesting that. James was too quiet in the previous videos, so today we're gonna make James nice and loud and in good quality. And so for me to also hear him, I need to put on the headphones now. All right, hit it! James, let's go!
In this lesson, we'll cover in greater detail how programs use accounts. Everything in Solana is an account. Even programs.
Yeah. As the saying goes, everything in Solana is an account. Yep. Everything is an account. Programs are accounts. Wallets are accounts. Data accounts are accounts. I mean, the saying is not 100% true because a transaction, for instance, is not an account. A transaction is just something that uses accounts. But it works on accounts. Everything that is persisted, everything that is in Solana state is accounts.
Programs themselves, however, are stateless.
So that's actually good to know, right? Because on other blockchains, this is different. Like EVM chains, you usually have the program with some state. So the program and it has some variables. On Solana, programs are always stateless, which means if you deploy a program, it will always be just the same program. It doesn't have any variables. All the variables and state stuff is stored in other accounts that the program then uses. But the program itself, it does not have state.
PDA.
PDA!
PDA stands for Program Derived Address.
Yeah.
As the name suggests, it refers to an address, public key, derived from a program and some seeds.
So a PDA is always derived for a specific program with some seeds, right? So if I have the same seeds but a different program, I'll get a different PDA. And I cannot derive a PDA without a program. You always need the program, which then allows only this program to sign for this PDA.
The purpose of a PDA is to create an address that a program can sign for in the same way a user may sign for a transaction with their wallet. When submitting a transaction to a program, the client needs to include all addresses for accounts that will be written to or read from.
Create a transaction, we need to say which of the accounts are being used and where we write and read from. And that means we need to know that on the client side. We cannot just call the program and say do something. We need to say do something with those accounts. If on the client side we just want to read some state, then we just need to know where that state is stored, aka we need to know what the account address is. And then we can just get account info for that account. Right, so how do we now create PDAs, James?
Finding PDAs. PDAs are not technically created. Rather, they are found or derived based on one or more input seeds.
That's what I said.
Regular Solana key pairs lie on the ED2559 elliptic curve.
That was the word, ED2559 elliptic curve. Thanks, James, for reminding me. I never remember that.
PDAs are addresses that lie off the ED2559 elliptic curve and therefore cannot be signed for by a private key, since there isn't one. This ensures that the program is the only valid signer for that address.
Since we're not on the curve, there cannot be a private key, and therefore we as the program are the only valid signer. So this paragraph essentially tells us how the PDA is derived. We know the program ID. We can choose the seeds. So that's either some string or another account, like a public key, or a combination thereof, string plus public key, or several public keys. That's up to us as developers, what seed we use. And then this find program address will also add a bump seed, which starts at 225, so a byte set to all once. And then we have a 50% chance of actually getting a PDA and about 50% chance of, being on the curve, which means we can't use that as a PDA. And therefore we need to just change our bump seed, which is just another byte that is added to the list of seeds. And we decrement it by 1. So the next bump seed is 254. And if that is still on the curve, again, 50% chance, then we decrement it once again. And this thing here, this decreasing the bump, actually this 50% chance, actually I had that be the error sometimes. If you're developing something and it works sometimes and sometimes it doesn't work, and if the ratio for that is about 50-50, then one reason might be that you don't use the bump correctly and you always have a 255 bump or whatever. Because if you always just have the 255 bump, then in 50% of the cases, you'll be right. But in the other 50%, you would have to use a different bump. But yeah, that's just mention that because that happened to someone that I know. Anyway, eventually, when we derive this, we will find a bump such that the address is actually not on the curve. So a byte is definitely enough for that, right? We have 255 chances and always a 50% chance of succeeding. So I've actually never seen a bump that is below 153. I've seen 255, you see a lot. 254, you still see. Much rarer, 253. Not like I look at all the bumps of all the accounts. But anyhow, do we now understand how PDAs are found? I think so. I think we're good here.
This way, the address can be generated anywhere as long as you have the bump and seeds.
So this find program address function method. We're not consistent here. Once we say function, then we say method. Anyway, it depends on your programming language, I guess. Find program address returns you the address it found, so the PDA, and also the bump that it used. Find program address will also give you the bump. There's another one where you just provide the seeds and it doesn't do anything. I think that was get program address, right? So we find program address, we get one where there is a private key for it because it is on that curve. So we add the bump. We already had the bump here because you can create a PDA without providing that last byte as a bump, but that is then a different PDA than if I were to add the bump with 255, because obviously I have a different seed, because the bump is also part of the seed. It's the last byte in the seed. We usually already have the bump here, and here we just change the bump to get a different PDA that is then off the curve.
Why does this matter?
Well, yeah, obviously, because the PDAs, those are the accounts, they will store our data. So that's what we use to look at our data.
If the client wanted to read data from this PDA, it could derive the address using the program ID and this same seed.
Well, we have some program code. Do we want to start with some programming? I guess we want to start with some programming. Because obviously, if you just look at code, you are not going to become a programmer. You need to actually write code / use code, because 90% of programming is copying code, but you don't have that from me. Okay, let's go. So we're just gonna do some stuff. Solana Web 3. We just need the public key, and then the public key should have a find program address. Okay, cool. So the new way to do it would be to not await, but have this sync. Cool, and we get back the public key and the number, so the PDA, public key, address, and then the bump. So our program ID, our program. Okay, it needs an array here, so we're just gonna make this an array of seeds. Yes, stuff changes quickly, or I didn't use the same method as James did. But I'm gonna use semicolons. So if we do that, we get back a PDA and a bump. So just for our pseudo program and a random seed, we would now get the following PDA, maybe to base 58 to make it readable, and the following bump. Let's check that out. If we say module 1.5, if we execute that, we get back an error. Classic. Invalid public key input. So we're just gonna use an actual program address that James has deployed probably. So let's use this. Why not? Just some random. This is a valid address now. So if we now do this, there we go. Now we get an address. So this is where the PDA would live, and a bump. Oh wow, we got 253. So we had to go through 2 times of decreasing the bump before we actually got this address. Maybe just a little bit into detail. There is create program address. That's it. Not get. Create program address, and probably also a sync version of that. That one, fun fact, will not handle the bump automatically. If we have a look in here, all we get back here is the public key. So we need to provide all the seeds. And to make my point from earlier, if we were to put in the same seeds and the same program ID, we will get back a different PDA here. This is now a different address. Why? Well, because we didn't provide a bump. We need to additionally, in this list of buffer, add the bump. Can I just do this? And then let's already use the right bump. Boom! And there we go. We get the same address now because we added another byte with a value 253. So this is just adding to the list of seeds. And the find program address does this automatically. Add a bump with 255 and then check if that's on the curve. There must be like a public key is on curve. Haha. And we can check if that is on the curve. This will give me true or false, and it will tell me that this is in fact not on the curve. But the previous ones, if we do this again and again and again with the bump seeds 255 and 254, then we will see that, all right, so, okay, so it doesn't even give me back an address. It just tells me you can't even use that list of seeds because it's not on the curve. So apparently this already calls the is on curve somewhere internally. So never mind. We can't even do that. However, the fun fact was that without that seed, without the bump, it would already be off the curve. But we can't guarantee that. For another address, it might not be on curve. So remove that again. Or let's do this. Without that bump, it would be off the curve, right? Just execute this again. Yep, those are not on the curve. Let's say if I had a different string here, like global state like this. Yeah, now it is on the curve, and then this gives me that invalid seeds thing. And that's exactly why we need the bump to be able to then guarantee that eventually it falls off the curve. Enough of that. Coming back to the good old James's course.
In more complex programs that store user-specific data, it's common to use a user's public key as the seed. This separates each user's data into its own PDA. The separation makes it possible for the client to locate each user's data by finding the address using the program ID and the user's public key.
Yeah, so this is common practice. We want to store some stuff for every user, or more specifically for every calling address. To be able to do that, we essentially create what you might know as a hash map, where you have the user's public key as the key, and then the PDA or the contents of the PDA as the data. So for every user that does something with our program, we just take their public key, get the bytes for that, and use that as our seed. So that would then look something like, oh, we don't want to create, we want to find. Let's do find again. Let's use a PDA3. So we would use maybe some user data as a string, and then the user public key. Maybe I do that. And let's say my wallet that I had here for whatever reason when I played with sugar. So my wallet, and then I can add this to the seeds, or I can just use this user public key to buffer, because here we have a list of buffers. Buffers just represent bytes. And so to our list of bytes, we first put a string and then our public key, and then we again nice PDA with some nice bump. Fuck. There you go. This time the bump is 254, and that's our address. Now this, of course, will be always the same when we call it with the same user public key. But as soon as the user public key changes, say I had a sugar here, so that's a different input key. Therefore, obviously, the address for the PDA will also be different. Wow, we actually got a bump that is below 250. Yeah, so this, we had to retry quite a lot. And that's also maybe already one reason why those bumps should be stored somewhere. So it has become good practice to store those bumps in the accounts, because that way in the program itself, so not in the front end, it doesn't really matter if we use find program address, whether we go through it twice or 3 times, we don't care. But on chain, we really want to save that compute, and therefore we don't want to, find the address every time. We might want to just already have the correct bump stored somewhere, read that, put that in. That's quicker. So that way we have a different PDA for each of the users. You can have several seeds or parts of the seeds. You can make your seeds pretty long, is my point, right? So you can first take the public key, or like we did, first take some static data, like a static string, then take a public key, and then add another bit, maybe like for each, if we want to store nodes, like in this example. Depending what you want to do, you might want to use different seeds here. So, or for instance, if every user has a treasury PDA or data, whatever, then maybe we just create the one with different seeds, like the one with token, and then the second one with data. Or what did we have? Treasury. We might have a treasury PDA, we might have a token PDA, we might have a data PDA for each user. Point just being, if the seeds are all the same, then the PDA will be the same. Easy. Okay, moving on.
Getting multiple program accounts.
Getting all the accounts from a program. That get program accounts was used, for instance, to get all the NFTs for one collection. And the way that was done, you get all the accounts from all the NFTs ever, and then you check if some field in the account matches, which is not very efficient. So again, we want to try and avoid this get program accounts, in my opinion. But just so you know what it does, we can give it a program ID and then check all the accounts it has. Ignore all of that part for a bit. And then we need a connection. And if we use a public endpoint, like if we call get program accounts on the public, let's check all accounts for this program that James did, it would probably tell us that we're not even allowed to do this and tell us shit. Okay. And so either you do this and then for each. This should be a for each. I have it double now. So this is how I would do it. I don't like the writing dot then. So maybe, here we go. I can't wait. We need an async function first. There we go. But apparently either it just doesn't work or this program doesn't have accounts. Yeah, because this program doesn't even exist on mainnet. Okay, but does it exist on devnet? Yeah, because we're devs. We work on devnet apparently. Okay, cool. Check devnet. There we go. Look at that. Now we got the list of all the accounts. So we get the account public key and the data, which is both not locked pretty, and the account data, well, since I don't know in which format it is, I'll leave it as a buffer now with the individual bytes. One more time. We see we have accounts. Those are all the PDAs. And then inside all of them, there is some data stored. Yeah. And we can already see that the data has different length for different accounts. We can also already see that some of the things seem to be quite similar. So there's always the 1 as the first byte, and then there's always 3 zeros here. So that makes me think that this always belongs together, those 4 bytes, and those 4 bytes, little endian is a 4. So maybe 1, 2, 3, 4 is this string. And then here we have another length of 11. Never mind. I don't know what is back here, but this here I assume is the length for what comes here. And if all of that does not make any sense, that's because you don't understand how serialization actually works or what it does in the background. But we will get to that today, hopefully. But we will see what this data actually stands for. We will figure that out in the course of this course. We could get all the accounts for that program. Now, finally, we get to deserializing custom account data.
Data property on an account info object is a buffer.
The buffer we need to decode to have, our strings and numbers back to use it more conveniently.
Deserializing requires knowledge of the account layout ahead of time. When creating your own programs, you will define how this is done as part of that process. Many programs also have documentation on how to deserialize the account data.
We need to know what those things actually stand for, right? They have been serialized somehow and stored in there. I mean, last lesson we serialized instruction data, but it's the same with account data. You also have to serialize it to store it, and then we deserialize it to work with it. For instance, one of the most used programs that I deserialized are from Metaplex, because I do work with NFTs a bit. Programs, token metadata. If you go to accounts, here they provide a nice list how those individual accounts are actually serialized and deserialized. So for instance, the metadata account has all of these features, and it tells us which seeds are used to derive this PDA. So the literal metadata, then the program ID of the token metadata program, and the token mint. So that's the SPL mint public key. Those 3 things are put together to derive the PDA, and then stored in the data of the PDA. Here are those things that we have a key at first, and the update authority, the mint, and so on and so on. And they even nicely say how big all of those things are and what the offset would be to get there. Anyway, first, the basics.
Otherwise, if the program code is available, you can look at the source and determine the structure that way.
Yeah, you can always, if it's not like documented, then you can look at the docs, then you can look at the source. For instance, the Metaplex programming library has the token metadata, which has the program, which has in source maybe some state. It's always in state. State defines the layouts for the individual things. And here, for instance, we have token metadata account, also a Borscht. There's the metadata struct. Here we see once again how that's built with a key, the update authority, the mint, the data, and so on and so on and so on.
To properly deserialize data from an on-chain program, you will have to create a client-side schema mirroring how the data is stored in the account.
Essentially, we can just create a schema with Borscht struct, and then all those Borscht thingies, a bool, a U16, and a string. And then, if we have defined that, with decode, we can put in the buffer and decode this thing, just like that. We would go player ID, name, and here again, though this thing refers to this, this to this, and if I were to do that, let's say I were to do that in here for the actual buffer of the account data, player ID, it's not gonna work properly for the name because this is not actually a string. The string comes first. So this will not work. It will probably think that we have a string that is too long. Yep. Nope. Let's see. Yeah. It would just take everything, the rest as a string. But that's not really what we have in here, right? But yeah, if I were to read the first byte as a bool, then all those ones would give me true, true. And if I were to read the second thing as a player ID, then I would read 4 in this case. So I take 2 bytes here, here would read 2. But really what this schema looks more like is that there is one string and then there is another string. Let me see how wrong my guess is by not doing this, but having string 1 and string 2. I don't know what they're named, but let's go string 1, string 2. That already looks better. There we have 2 strings. Build says Kyle. Megazilla says I want money. So yeah, always fun to read what's on chain. I love it. Who cares? Let's see if I can call this string 5 and then call this string 5. Then I get undefined. So because we deconstruct that as an object and not as a list, this name must match this name. Just for testing purposes, I tried this out. Moving on.
As a refresher, this project uses a Solana program deployed on DevNet, which lets users review movies. Last lesson, we added functionality to the front-end skeleton letting users submit movie reviews, but the list of reviews is still showing mock data. Let's fix that by fetching the program's storage accounts and deserializing the data stored there.
Yes, let's.
1. Download the starter code.
And solution serialize instruction data is the one that he wants us to use. I think I did that already. Quickly git stash my stuff and then git check out this. Ah, that looks good. Okay, cool. Which means our Solana movie front end should now be in the right state. That's what it looks like. The demo, we have the starter code. The project is fair. Yeah, we know that from last time. So now we create the buffer layout. Okay, so we have a boolean, a byte, a string, and another string. Okay, so in the movie class, that's the instruction schema that we did last time. And then we want to have a static Borscht account schema, which will follow the same rules. We just use a Borscht struct. We've included project serum Borscht, and we're gonna use a Borscht bool. Think that's that. Did we do that right? I think we did that right. Remember, order matters. Yes, because if we have the rating before the title, then obviously that 1 byte comes before the length for that string. Now let's create a method to deserialize data. We have the buffer layout, and let's create a method deserialize that will take an optional buffer and return a movie object or null. We create deserialize, which will take a buffer. It return either a movie or null. Borscht account schema decode buffer. I need to put some question mark here. And then if not buffer, return null. We decode that, and that will give us back, how was that? We now decode that, and then we return a new movie with the title, the rating, the description. And the initialized, well, I guess we ignore that. We could do something like if not initialized, return null or whatever. So that would be my solution for what is written here. And James does it the same way. Cool. Let's fetch some actual movie review accounts. In the movie list, instead of those mocks, we say actual movies. Wait, let's call them on-chain movies. We get them by, let's just make a new connection. And then say get program accounts for my movie review program. And this will get me my, so new public key, get program accounts, returns us a promise, but I can't await in here apparently. I mean, I could make this async. Maybe we do it the James way. Then, when we get the promise, we'll have accounts that we map accounts for each of those accounts. Yes, for each, not map. And each account consists of a pub key and account. Okay, you do the following. And the account we need to read the data from. Account data has the buffer. And then we just need to put that into the movie.deserialize, which takes a buffer. So the account.data, boom, which returns us our movie. And then we just map, because then what we get back here is an array of movies. Set movies for our on-chain movies. You know what? Then we also just filter there we go. That's how you do it. So we filter for movies. Now we get a proper movie array because we remove all the nulls. But yeah, he then also has everything in one line. Then, oh, he uses the async. Okay. Looks similar to what we have. At this point, you should be able to run the app and see the list of movie reviews retrieved from the program. And then we see, oh, see, there's different one. There's a test, a Duna Awesome, a 7.5, Andy's Solana dev course, which is pretty good. Wait, did I write that there? I guess I wrote that there in a previous lesson. There. Andy's Solana dev course part 2, which is pretty shit. Super shit. This actually went through and it's now on chain and you can't remove it. The next part would be to do pretty much the same thing, but with the student intros. And let me guess, you have an initialized and 2 strings. Yes, we have as we had it here, or if we look here, we have two strings, and now we also know what they are. They are name and message. And then we have name and message. Name, and message. And that is pretty much all that James's course tells you to do. Now, if you were able to follow me so far, do the challenge, do this thing, do it once yourself, such that you get the hang of it with this whole, creating the schema and then calling the decode. But it is pretty simple. What I now want to do with you in the last few minutes of this class is go a little bit more complex. So, first, let's discuss how this serialization actually works. Essentially, here we're looking at Anchor documentation, and it tells us how much space we need to allocate for certain data types. For instance, for a Boolean, we need 1 byte because it will only ever use 1 bit, but it still needs the entire byte. So that's what we saw here. It will only ever use the 1 bit, it's 1 or 0, but it will use an entire byte. A bool will always have 1 byte, a U8 will always have 1 byte, then 16, 2 bytes, 32, 4 bytes, 64, 8 bytes. That all makes sense from the, the bigger it is, the more bytes it takes. Then if we have arrays, they have a fixed size, right? So Porsche array, that would be this. So there we have the space for one element multiplied with the amount of elements, which makes sense. If I have an array of 2 U16s, then it takes 2 times 2 is 4 bytes, because arrays just have the fixed length. Okay? A public key will always have 32 bytes. A vector, and now it starts to become interesting, has 4 plus the space one element takes times the amount. By the way, if you don't know what a vector is just a dynamically sized array. So it can have an arbitrary length, and therefore we need to save the length of the vector. So how many elements are gonna appear, and that is done in a U32. So 4 bytes are allocated for the length of the vector, and then we have for each item, how many items there are, times the space as the fixed length. If I have a vector that I encode, then I first encode the length in 4 bytes, and then I have the individual elements. So T just stands for any kind of object. String, same thing. We first have 4 bytes, so a U32 for the length of the string, and then the actual string. There are other ways how we can represent the string. We can have the string bytes and then ending with a 0, but that has the disadvantage that we need to go through the entire string until we find the end. It's much nicer to, in this case at least, to have the length in the very beginning, because then we just need to read the length and then we can skip that many bytes. So whatever number we read here in bytes, we can skip to get to the next element, or that number of bytes we need to read to get the string. And then an option, that's also interesting. We have 1 byte, which indicates whether or not the option is present. So it's an optional, and then just the thing itself. So if the first byte is set to 1, then yes, what follows is that thing that is optional. And if it's set to 0, then no, there's no more bytes. Then it's just 1 byte for the option. What I wanted you to understand here is that a string and a vector always has this leading indication of the length, and an option has this leading whether or not the option is present. You are responsible for how the data looks on chain, right? So on the account itself. Metaplex has, for the name, they do not encode it as Porsche would do it if you just put in a string. They say the string has a maximum length of 32, and we will always allocate that amount of bytes, so the 4 plus the 32, for that string. So no matter how long the string actually is, the next thing will always start 36 bytes later. Why would you do that? Well, to have a fixed offset. So when I want to read the symbol, I always go to the 101st byte in the account. If I want to read the update authority, I always go to the first, the mint always to the 33rd, name always 65th, symbol always 101st, URI always 115th. So even though those things are variable length, it doesn't matter because we just allocate for the maximum length of them and proceed after the maximum length. Okay, so that's just some theory. What does that mean? I essentially want to prepare you for manually decoding account data and not relying on Borscht. Like, I mean, the Borscht account schema like this, that's fine. But if I don't want to do it with Borscht and I wanted to do this manually, I want to show you how it's done manually, just so that you appreciate how helpful Borscht is. So we're going to do the same thing here, except we're not going to use Borscht anymore to decode. We're going to do it manually. And we know that we have a buffer because we checked that it's not null. So the first thing we get is the initialized. That's not too hard to get because it's literally just the first byte. So we can just call from our buffer at offset 0. So far so good. That's pretty simple. Then comes a U8. Okay, also not too hard. And this time we have an offset of 1 because the first one was already this. That's 1 byte. So the next thing we read is with offset 1. Okay, so far so good. Now we read the title. Okay, const title. Because we don't know how long the title is. So first we need to find out the title length. And we do that by reading an int 32 with little endian. Solana, always little endian. Something like this here. It's 4 bytes that we read with the offset of, correct, 2, because we got another byte here. Now we have the length. Okay, which means we can get our actual title, which we can get with a new string. I'm not actually sure if I can get a string from a buffer. We'll have to try that out. But anyway, where is that string now stored? Well, it's in the buffer. Let's do a slice to just get the relevant part of this buffer. Where do we start? Which offset? Well, we already had 2 as an offset, and then we read 4 bytes. So 2 plus 4 is 6. 6 plus the title length, because each character in the string is 1 byte, and the length defines how many bytes we need to read. Since we use it twice, make an offset like this. Or we could do like a let offset, set it to 0, then do offset plus plus. Yeah, let's do that. Start at 0. We read at 0. We say offset. We read another one. We again say offset plus plus because we read 1 byte. And then we read another one. And then we say offset plus equals 4 because now we read 4 bytes. So offset should now be 6. And then we have 6, comma, and 6 plus the title length. Is that easier to read? Not really. Okay, so this seems to work. We should be able to get a string from a buffer slice. Maybe, I'm not sure. We'll have to check. And then we do the same thing again. But what is our offset now? We already added those 4 for the length. And now we read another title. So we add that to our offset. And then we do essentially the same thing like we did here. We read the length is again read 4-bit integer, add those 4 to the offset, and then read a new string description from the offset to offset plus description length. And now we could also assert that our final offset, which is the offset plus the description length, is actually the same as our, because we should have now reached the end of the buffer. And then new string to string, because that makes perfect sense. Why not? Let's do it. Okay. Let's see if that actually works. No, it doesn't. It just temporarily didn't compile. Okay, successfully compiled. Not assert. I mean, I can console log offset buffer length, because I made it static. Yes, it does. And yeah, we can load it. And the Solana dev course, which is pretty good. Pretty good. And just to prove that this is actually what we are doing here, we could do something, read that string -2. We don't read the entire string, but we drop 2 characters just so you see, core, the dude is not here anymore. So remove that again, run it again, load it again, Duna. It wasn't the dude, but it was Duna. Yeah, so that's how you manually read the state without using a Borsch schema. I think I want to end it here. Decoding, deserializing some accounts. And we talked about PDAs in the beginning. If you want more information on PDAs, I also have a separate video on that. Also, there's a really good Solana Bytes video on the topic of PDAs. Then I shall see you in the next class. Yes, because now that we are done with this, there's only page order and filter custom account data left. So one more class until we're done with module 1 of 4. How nice. Well, I hope that you learned something today. I wish you happy coding, and I will see you in the next tutorial. Check out those other videos. Subscribe if you haven't already. Like the video. Let me know if you like that sort of content. I now got professional lighting setup, or semi-professional, and my semi-professional green screen. So my video quality is also increasing, I hope. Thank you for watching. And yeah, just stick around in our journey of learning Solana development. I have a bunch of more videos coming up. I can finally make videos again and provide you with quality content. See you next time for more quality content. Yeah. Such quality. Much quality. Much wow. Oh man, I'm an idiot.